Hi everyone, this is the first video in the series The Art of Modular Arithmetic, and all the reference material that we need for this series is in this link right over here. So this is the book The Art of Modular Arithmetic, and the URL will be in the description as well. So let's open this book up and let's start with chapter 0. So the first thing that we have to know here is the notation that we'll be using throughout the book. And so in terms of notation, most of the notation is just general math notation, things that you would encounter in your math class or in your math textbooks. But some of the notations is more special. Some of the notations are more specialized. So let's talk about the more specialized notations. So first, the first kind of specialized kind of notation that you have to know is z to the c. That's my best z that I can do, but z, is the set of all integers from like regular math textbooks or regular math notation. And so if you put a c now, then the way that this book defines it is that z to the c will be the set of all integers, but under some constraint c. So for example, if you have z to the greater than or equal to 0, then you know that that's the set of all non-negative integers, or the set of all positive integers as well as 0. So if you want to write this out, then you could say that this is 0, 1, 2, and so on. It's that infinite set of integers. And for example, if you have something like this, so you have z to the, let's say 2, 9, then this is the set of all integers in the interval from 2 to 9, that is inclusive on both ends. So this would expand to 2, 3, 4, all the way up to 9. And you can really put any constraint that you want here. You can put any notation, any constraint, and it will be assumed that z to the c just means any, like all the set of all integers that meet those constraints. So now the next notation is a comma b, and what this means is basically the least common multiple of a and b. So sometimes you'll see this written in textbooks as LCM and then a, b with these square brackets, or some textbooks might also write as capital LCM and then use parentheses. And there are many variations of this, but the underlying idea here is that this is just the least common multiple, and it's assumed that you know what the least common multiple is, and we won't really go into like that much depth to define it. But whenever you see square brackets, you can assume that it's the least common multiple. But in some contexts, for example, like the context that we just discussed earlier, for example, when you have z to the 3, 9, then in this case, 3, 9 here, this isn't really a least common multiple, this is an interval that is inclusive on both ends. So based on the context, you should be able to tell whether we're talking about an interval or whether we're talking about the least common multiple. Greatest common divisor, and it's similar to least common multiple in the sense that it's also a comma b, but instead of using square brackets, we're going to be using parentheses. So we'll have parentheses a comma b, and again, to differentiate this from an interval that is exclusive on both ends, you would need to use the context. So if there's like a z here, then you know that it's talking about the interval, for example, but if it's just by itself, then you know, or you can infer that it's talking about the greatest common divisor. So some textbooks might also write this as GCD of AB, or, capital GCD of AB, or any variation of this sometimes. But to keep things simple here, we're just going to be using the parentheses because LCM and GCD will be using a lot, so it's convenient to just have simpler notations to express these. Now let's move on to floor and ceiling. These are fairly standard. You can even encounter these in most math textbooks, but it's worth going over because these notations are slightly non-standard. So now first thing we have is the floor of x, and in some textbooks you'll see this written as x with just square brackets around it, but this is kind of like, this notation makes it kind of vague. We'll be sticking to this notation here. So this is the floor of x, and for those of you who don't know what the floor is, it's basically just the greatest integer function, or in other words, the greatest integer that's less than or equal to x. So for example, if we have the floor of pi, then you know pi is, so you can think of pi as 3 plus like a fractional part basically, so 0.1415 and so on. And basically, so this is the integer part here, and this is the fractional part. And all we really care about when we're talking about the floor for a positive or a non-negative number is the integer part. So we're just looking at 3. And that's a good shortcut to know. But now when we, so for example, now if we have 2.7, then this would be 2. And so on. But now if we have something that's negative, or let's talk about 0 first. So now if you have 0.9, this is 0. And obviously the floor of any integer is just going to be itself, because the greatest integer less than or equal to an integer is just the integer itself. So for example, if you have the floor of 2, then you're just going to get 2, and so on. But now let's talk about the negative numbers, because these are slightly less intuitive. So when you have a situation where, for example, you have negative 0.9, right? Then you might be tempted to say that because 0 is the integer part of negative 0.9, or it seems like it's the integer part of negative 0.9, that it would just be 0. But actually, we're talking about the greatest integer less than or equal to, and 0 is actually greater than 0.9, or negative 0.9. So we should be saying that this is actually negative 1. And this is kind of not intuitive because you don't really see a negative 1 here in this decimal, but it is negative 1 because we always need to go down when we're talking about the floor. And for example, if you have the floor of negative pi, then for the same reason, because it's less than negative 3, we need to go down to negative 4. And like in the positive case, if we have the floor of negative 2, for example, then we're just going to be dealing with negative 2. Or if you have the floor of an integer, then it's just going to be that integer itself. So you can just remember that the ceiling of x is the least integer greater than or equal to, because you can see you can see that these ceiling brackets over here are pointing up like this. So that just tells us that it's the least integer greater than or equal to. And so now this is kind of like the opposite of the floor. So when we have a positive number such as, let's say, pi again, and we want to look at the least integer greater than or equal to, then because pi is 3.1415, so on, the least integer greater than or equal to this is 4. And now that that's taken care of, let's move on from the notations to some sample problems. And these are sample problems that are kind of function as prerequisites for the material that we'll be getting into. So it's a good idea to know at least how to approach these problems. These are obviously on the harder end. They aren't necessarily things that you would see in school very often, but they are worth going over to make sure that you understand the prerequisite material. So they kind of establish a baseline. So let's go first into the first problem, and this is asking us, what is the largest positive integer that divides 40 and 78, and what about the smallest positive integer divisible by 40 and 78? So when we're talking about divides and divisible and all of these things involving division or factoring, then we always look at prime factorization. So let's look at the prime factorizations first of 40 and 78, and then look at how those can guide us to understand, to make sense of this problem and really understand what it's getting at. So first, for 40, well, the most obvious factorization that stands out to me at the moment is 4 times 10, because it's just a 0 at the end. So 4 we know is 2 squared, 10 we know is 2 times 5, so we can rewrite this as just 2 cubed times 5. And we know 2 and 5 are prime, so this is our prime factorization. Now let's go into 78. 78 is a little bit harder to visualize here, but we know 8 is an even number, so 78 is also an even number, so it's divisible by 2. So we can say that this is 2 times 39 when we do the division. And 2 times 39, so 39 is a little bit tricky again, but 39, I see that 3 and 9 are both divisible by 3, so we can pull the 3 out. So we get 2 times 3 times 13. And we know 2, 3, and 13 are all primes, so 2 times 3 times 13 is our prime factorization for 78. So this is our prime factorization for 40, our prime factorization for 78. And I'm just going to circle these so we know what we're referring to here. Those are prime factorizations. And now let's think about what is this problem asking us. So it's asking us first to determine the largest positive integer that divides 40 and 78. So we want to look at something that divides. So we want to look at the factors that are in common, or essentially the factors that are here for 40 and for 78. And we want the largest positive integer that divides 40 and 78. So for example, for 2 cubed and 2, we have to choose the power of 2 that is just 2 itself, or 2 to the power of 1, because if we choose any other power of 2 that's greater, then we won't be able to divide into 78 anymore. So effectively, when we look at this greedily, we have to choose the powers of 2 that, the smallest power of 2, so that's just 2. Or the largest power of 3 that divides both of these is actually 3 to the 0, or 1, because you see that there is no power of 3 in our prime factorization for the first thing here, so there's actually just, you can think of it as a 3 to the 0. And between these two, 3 to the 0 and 3 to the 1, which one is smaller when we're looking greedily, is 3 to the 0. So we don't need to circle anything here, it's just 3 to the 0, which is 1. And now the next thing that we need to consider here is 5. So for 5, again, just like 3, the largest power is just 5 to the 0, or 1. So we can't really look at that. And then 13, once again, we have the same problem. There's only a 13 here, there are no powers of 13 here, so the greatest common divisor for that is just 1. So now, when we look at this, then we can say 40, the greatest common divisor, or the largest positive integer that divides 40 and 78, which we call the greatest common divisor, is 2. So we can say that the GCD of 40 and 78 is 2. Okay, now we're back and we have the prime factorizations rewritten, and I erased all of the work that we did for the greatest common divisor, which answered the first question. But now let's look at the second question. What about the smallest positive integer that divides, that is divisible by both 40 and 78? When we're looking at something that's divisible by a bunch of stuff, we're looking for a multiple, basically, or like a multiple of that stuff that we can create. And in this case, we want the smallest positive integer that's divisible by both of them, so we're essentially looking at the least common multiple, or LCM. So in other words, we want to look at the LCM of 40 and 78, or we can just rewrite this using our notation as 40, 78 with square brackets. And let's look at how we can find the least common multiple now. So for the least common multiple, we always want to look at the smallest powers. We want to look at the smallest powers of each of the prime factors such that the number that we're producing is a multiple of them. So for example, let's start with the powers of 2. So we have 2 to the cube, we have 2 to the 3, and we have 2. So now if we want the least common multiple of this for this prime factor, we have to go for the largest exponent, because if we choose anything smaller than that, then that's not going to be a multiple of the largest exponent. So we need to go for 2 cubed. And then when you look at the powers of 3, there's a 3 to the 0 here, which is 1 again, and then there's 3. So when you're looking between 3 to the 0 and 3, the larger power of is 3. And similarly, the largest power of 13 is 13 itself, and the largest power of 5 is 5. So that tells us effectively that the number that we're looking at here is 3 times 2 cubed times 13 times 5. That's our least common multiple. And you can evaluate this if you calculate it out. And that answers our second question of the least common multiple. Now before we move on, there's one important note that we have to make here, and that is that if we look at this, the first part we looked at the largest positive integer that divides these, and we said that that's actually the greatest common divisor of 40, 78, or just 40, 78 in parentheses if we use our notation. This should be a 0. 40, 78. And we said that this was 2. And then we said that the LCM of 40, 78, or just 40, 78 in the square brackets using our notation, we said this is 1560. And if you look at these two numbers, they're actually like very opposite to each other. This is very small and this is very big. And you think about it a little bit, and what you realize actually is that if you multiply the GCD and the LCM together, so if you have, we can just use our notation here, so if you have 40, 78 in parentheses times 40, 78 in square brackets, or the GCD times the LCM, then what you end up with actually is the same thing as 40 times 78. And you can work this out. If you do 2 times 1560, you'll get the same thing as 40 times 78. And if you think about it, this is actually a really interesting property. And it turns out that this does hold in general. And we won't really prove that here, but you can look up a proof, and it's not that complicated. It does involve looking at the prime factors. But we can say in general that a comma b, the GCD of a and b times the LCM of ab equals ab. And this is a property that generally holds true for all a and b. And this is a property actually that would make this entire process a lot easier. And we'll talk about how in a later video. But first, but for those of you who are curious, basically to calculate the GCD, we can use the Euclidean algorithm, and then to calculate the LCM, we can just say that that is the first number times the second number divided by the GCD, which is a comma b. So this would be our LCM, a, b. So if we use the Euclidean algorithm to calculate a and b, and the GCD of ab, then we can just use this formula, and then we will easily be able to figure out the LCM of ab as well. So now let's move on to the second problem. A 6-place number is formed by repeating a 3-place number, for example 256, 256, or 678, 678. Find the GCD of all numbers of this form. So now this is an interesting problem because we're directly referring to the GCD. And this problem is also from the 1959 AHSME, which was like an old version of the AMC12, and it's the number 19 problem. So it's actually like it's actually at a fairly later point in the test because it's obviously not as like direct or intuitive as a problem as some of the other ones. So now let's think about this a little bit. So we're talking about a 6-place number, so that just means a number that has 6 digits in it. So we can think of it as ABC, ABC, because we're repeating a 3-place number or like a 3-digit number. And the way that we're going to write this is ABC, ABC with a line underneath, so like this. And this line underneath just means that we're talking about digits here. We aren't talking about a times b times c times a times b times c. We're talking about the number a, b, c, a, b, c. And if you think about this now, this is actually just the same thing as the number a, b, c, 0, 0, 0, plus the number a, b, c. Because you can just think of these last 3 digits as their own number, and you can think of this as a, b, c, 0, 0, 0 when we move out those last 3 digits like this. And actually, this is actually a really interesting thing because now we can think of the first number here as 1000 times ABC. And then we do plus ABC. So we have 1000 times ABC plus ABC. That's the same thing as 1001 times ABC. Or we can just say 1001 ABC. Keep in mind that 1001 is here being multiplied and it's not like a part of the number itself. So it's 1001 times ABC. So now if you look at this, we want to find the GCD of all numbers of this form. So we're looking for the GCD, or the greatest common divisor. But if you think about it, we don't really know, we can't really say anything about the number ABC here. It's just like it can be any random 3-digit number. And a lot of like, if you look at the GCD of all the 3-digit numbers overall, it's just going to be 1 because a lot of them will be relatively prime to each other, or basically they won't have any divisors in common. But if you have 1001 times that, then this is going to be all of the 3-digit multiples of 1001. So the only factor that they'll have in common here is 1001, and this is actually the largest factor. So 1001 ends up being our GCD, or our answer. So we can box it here. Now let's go to problem 3. So one of the first 1, 2, 3, 4, 5, 6, 7 positive integers is chosen at random. Compute the probability that it is divisible by 3. So 1, 2, 3, 4, 5, 6, 7 is actually, it looks kind of like a scary number. It's very large. It's very daunting. So let's look at this one step at a time. So we have one of the first, a bunch of like positive integers, and we want to find the probability that's divisible by 3. And we don't really know immediately what to do, so let's just try something else. So let's just start listing these numbers and see if we can find any pattern in them. So let's start with 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to run out of space here, so I'm just going to say dot, dot, dot. And we're going to do this all the way up to 1, 2, 3, 4, 5, 6, 7. We obviously don't have the space to list all of these out, but that's why we put the dots here. So to indicate that it's continued on. So now we have this list here, and we want to know the probability that it's divisible by 3, a number that we choose randomly, and if it's divisible by 3. So we have to figure out basically the number of these numbers that are divisible by 3 when we talk about, so let's look at what probability actually means. So we want the number of these divisible by 3 divided by the total number. So the total number here is just 1, 2, 3, 4, 5, 6, 7. So the denominator for our probability is just that huge number there. So now we need to somehow be able to count how many of these are divisible by 3. So let's start looking, and let's just try to see if we can find a pattern. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and we've circled 3 numbers so far. And we'll continue circling these numbers, but obviously we don't have the space or the time to do that, so let's just start looking at if there's a pattern in these. So you can see that after the first 3 numbers, we got 1 divisible by 3. After the next 3 numbers, we got another divisible by 3. After the next 3 numbers, we got another divisible by 3. So you can see there's a clear pattern here. Every 3 numbers, we get a number that's divisible by 3. And that's no coincidence, actually. That's just the definition of divisibility. So we have 3, 6, 9. And every time we yield another multiple of 3 just by adding 3, like that. So the number of these that are divisible by 3, we can just think of it as, okay, we have 1, 2, 3, 4, 5, 6, 7 total numbers, and we want to cut these into packages of 3 until we can't make any more. And we want to figure out how many of these packages of 3 can we make, because for each packet of 3, the last number in that package will be a number that is divisible by 3, so it should be included in this count. So the number of packages that we can make is just this divided by 3. But because it can be a decimal, we have to take the floor so that we round down. So we have the floor of this thing divided by 3. And what this will tell us basically is, that our probability overall is the floor of 1, 2, 3, 4, 5, 6, 7 divided by 3 divided by 1, 2, 3, 4, 5, 6, 7. And this, if you have a calculator, you can calculate it out. You can calculate the exact probability if you want, but if you want an approximate amount, you can say that because we have every 3 numbers, we have one number that we care about, or one number that really contributes to our probability, we can say that this is approximately 1 in 3, or 1/3. And 1/3 you can expand it out as 0.3333, repeating. So this is going to be the decimal that's very close to this value, but if you want, you can calculate the exact value using this expression, and that's our answer. So now let's look at the next problem. So we have problem 4. Find all integers x for which it can be said that the positive integer 2x plus 9 divides the positive integer 3x plus 4. So again, there's a lot of information being thrown at us. Let's dissect this problem one at a time. So first we have integers x, so that already gives us a restriction here. X can only be integers, so x is in the set z. That we'll write like that. And okay, so it's all integers x for which it can be said that the positive integer 2x plus 9, so we know that 2x plus 9 is in the set of all positive integers. We'll just write that as it's in the set z plus, and we know the positive integer 2x plus 9 divides the positive integer 3x plus 4. So first of all, let's write 3x plus 4. We know that has to be a positive integer, so 3x plus 4 is in the set of z plus, using our notation from before. And we want 2x plus 9 to divide 3x plus 4. So essentially we're saying we want 3x plus 4 divided by 2x plus 9 to be an integer. So we want this to be in the set of all integers. So these are our constraints, and we want to find all x. So our goal here is to find all x such that all of these conditions are true. And this is a lot of information that we have at once. So let's start dissecting it one at a time. So the very first thing that we can think about is what can we say about x from the, so we already have kind of a value, we already kind of have a direct statement for x based on the first condition, but what can we say for x based on these next two conditions? So we can say 2x plus 9 is in the set of z plus, so we know 2x plus 9 essentially is greater than 0, first of all. And we know that means that x is greater than negative 9 divided by 2, so let's write that out. What's negative 9 divided by 2? Negative 9 divided by 2 is negative 4.5, so negative 4.5. And we know x is an integer, so if it's greater than negative 4.5, it has to be greater than negative 4 as well. So we know now x is greater than negative 4, and x is also an integer. So we can rewrite our second condition to make sense of that. Let's go ahead and write that. So we can say that x is in the set of z, the set of integers, greater than negative 4. So we can say, this should be greater than or equal to negative 4, because x just needs to be greater than negative 4.5. So it can be greater than or equal to negative 4. So it should be greater than or equal to negative 4. And now let's look at the next condition. So let's go ahead and erase this right over here. So our next condition tells us 3x plus 4 is greater. 3x plus 4 is in the set z plus. So we know 3x plus 4 is greater than 0. And 3x plus 4 being greater than 0, what does that mean for us? That means that x is greater than negative 4 over 3. What's negative 4 over 3? Well, negative 4 over 3 is like negative 1.3, so on. So it's x is greater than negative 1.3, so on. So it's greater than or equal to negative 1. So now we can go ahead and remove this. X is greater than or equal to negative 1. So x is in the set. Let's go ahead and remove this as well. So now from this, what we know is that x is in the set of all integers greater than or equal to negative 1. So now these are the conditions that we came up with, and now we have to think about, okay, what can we do next? Well, next let's find any redundant conditions, or conditions basically that are implied by other conditions that we don't really need to care about here. So first of all, x is in z. That's already kind of implied by everything else here, so we don't really need to worry about that. We can get rid of this. So let's go ahead and get rid of that. And the next thing here is that we know x is greater than or equal to negative 4, and x is also greater than or equal to negative 1. So, well, we know that if something is greater than or equal to negative 4, then it has to be greater, but we know that if something is greater than or equal to negative 1, then it has to be greater than or equal to negative 4. So we can also remove this condition right over here. So effectively, these are the only two conditions that we really care about. So let me go ahead and rewrite them for us. So this is what we have now. So just these two conditions, and this condition looks like it needs some work here as well, right? We don't really have a direct expression here for x yet, so let's try to figure out what we can do here. So 3x plus 4 divided by 2x plus 9. Well, if you remember anything from polynomial division, we can look at how many of these 2x plus 9s go into this 3x plus 4. So we can actually rewrite the top as 2x plus 9 plus something else, right? So we can say that this is 2x plus 9 plus x, and then we have a situation here where we have a 4 here, but we want a not, but where we have a 9 here, but we want a 4, so we just put negative 5 here. So it's 2x plus 9 plus x minus 5 divided by 2x plus 9. And we know that this is essentially just 1 plus x minus 5 divided by 2x plus 9. And now we know this has to be an integer, basically. That's what this entire condition has been telling us all along. So if this is an integer, then we know that because 1 is an integer and we need an integer overall, we can just get rid of the 1 here. And that just tells us that this thing right over here is an integer. So this is an integer. And we're in kind of a situation here. So we can't really divide anymore. So now I guess we have to start looking at cases. So we have x minus 5 and 2x plus 9. Let's go ahead and write that. X minus 5 divided by 2x plus 9. And the very first thing we can think about here is, what if this thing is, we know x minus 5 is, like, let's say that x minus 5 is less than 2x plus 9. If that is true, then we know that this can't really be an integer unless we know that x minus 5 itself is 0. So if x minus 5 is 0, then this entire thing just becomes 0, and that's really nice. And in that case, we would just have x equals 5. So if x equals 5, then this entire thing would just be 0, and that would be an integer, which would work out. But the issue here is that if x minus 5 is less than 2x plus 9, any of those other cases, then this entire thing won't come out to an integer. So what we really need to think about here is that we want x minus 5 to be greater than or equal to 2x plus 9, because we want x minus 5 divided by 2x plus 9 to give us some integer here, other than just 0, which is a special case. So we can say x minus 5 is greater than or equal to 2x plus 9, because if it's equal to, then we'll just get a 1, but if it's greater than, then we'll get some other integer that is other than 0. So we have x minus 5 is greater than or equal to 2x plus 9, and then let's go ahead and flip this around here. So 2x plus 9 is less than or equal to x minus 5, and we have x is less than or equal to, we have the situation here, so we have x is less than or equal to negative 14. So either x equals 5, or if this integer isn't 0, then we know that x is less than or equal to negative 14. So now those are only two cases that we have to worry about. So let's go ahead and go back up and put those into the conditions. So overall, what this condition has told us is that either x equals 5 or x is less than or equal to negative 14. Well, we know that x is greater than or equal to negative 1 from the first condition, so this is out. And so effectively, we know that the only value of x that can work for this, all of these conditions combined, is x equals 5. And that's our answer. So x is equal to 5, and that's the only possible value of x. Now our next problem here is prove that for all primes p, the smallest positive integer whose factorial is divisible by p is p itself. So let's see, all primes p, so we're looking at primes p. Let's go ahead and write that out as our condition. Primes p. And now, so we want primes p, and the smallest positive integer whose factorial is divisible by p is p itself. So we want n factorial divided by p to be an integer, basically. And we want to say that the smallest value of n for which this is true, we want to say the min value of n basically is equal to p. And we want to prove this. So whenever we have this kind of proof where we want to prove that something is divisible by something, or the smallest value of something is divisible by something, sometimes it helps to think about proofs by contradiction, which basically means we assume that the opposite is true for the sake of contradiction, and then we use math to deduce that actually if the opposite is true, then we arrive at a contradiction. So effectively, we have to have that the original statement, which is the problem itself, was true. So now let's look at this. So we have n factorial divided by p is in the set of z. And we want to prove that the min value of n is p. So let's assume for the sake of contradiction, we assume that n is actually less than p, that p is not actually the min value of n, that there is some n that's less than p that we don't know about. And we want to prove that, we want to basically arrive at a contradiction now. So we want to show that n factorial divided by p is actually not an integer. So if n is less than p, then what happens? Then we just get n factorial is 1 times 2 times 3 all the way up to n. And because of the fundamental theorem of arithmetic, what we have here is that all this entire factorization right over here will contain all primes that are less than n. All primes are less than or equal to n actually. So this factorization right over here will contain all primes that are less than or equal to n. And because we know that this is less than p, we also know that this will contain all primes that are less than p. And that is the only primes that it will contain. It won't contain p, and it won't contain any primes that are greater than p. So we know that this entire factorial right over here does not contain p. So basically we're saying that p does not appear in the factorization of n factorial, and essentially we're saying that p does not divide n factorial. So essentially we're saying n factorial divided by p is not an integer, and we've arrived at a contradiction here. So because of the contradiction, we know that the min value of n is p indeed. Now we have problem 6. So find a closed form for the remainder of a divided by m, where a and m are in the set of z plus. And we also have a footnote here. So if you download this book, one thing you'll notice is that we'll have some numbers in footnotes here, and that will just give you hints for some of the problems. So if you look at the footnote, then just be aware of the fact that it could be a hint, or it could be some remark that could potentially give away the problem's approach. So just keep that in mind. So our problem is asking us to find a closed form for the remainder of a divided by m. And this is kind of a complicated problem if you think about it, because we don't really know anything about a and m, but we just know that a here is being divided by m, and we want to find a closed form for this. And whenever we find, and we want to find a closed form for the remainder of this actually. So we want the remainder of a and m. So let's think about what happens when we, so let's say that we have a long division, right? Let's say we have m out here and we have a. Now we need to think about how many times does m go into a. Well, the only number of times that m can go into a is the number of packages of m basically that we can divide a into. And like we thought about before, that's just the floor of a over m. So that would be our quotient up here. And down here what we have is the floor of a over m times m, whatever that is. And so our remainder effectively would be a minus the floor of a over m divide a minus the floor of a divided by m times m. So this is actually our closed form for our remainder, and this effectively is our answer. And that concludes chapter 0. And so as you can see here, the hint actually was that your answer should involve the floor of a over m. So now if we cross-check what we have here with the hint, it makes sense that indeed we did use the floor of a over m. So that concludes chapter 0 of the Art of Modular Arithmetic series. So thank you so much everyone for watching, and if you liked the video, please be sure to like and subscribe for more content, and in the next video we'll be going into the next chapter.